it helps to visualize how our model is making decisions through this idea of a decision boundary. With a decision boundary, we can see if an observation lies in a certain space, what prediction will our model make? So let's run this block of code here. So we have an interactive visualization, we have a binary classification, and we can play around with the hyperparameters of the model. In this case, max depth and the min sample size, the min leaf size. So initially, if we have a very shallow tree, just a depth of 1, this is our best attempt to separate our two classes. And notice the cut is orthogonal. It goes along one axis, one dimension. Let's see what happens if we increase the depth here. So we increase the depth, and notice we have, this was our original space that it divided up, and it performed another division into our space. So notice what's happening here is that we're creating boxes, these orthogonal regions. Increase the depth, we perform more splits. You can also play around with the min leaf size. So one way you can view geometrically what is occurring in a decision tree model is that it's trying to box in the observations, isolate them. And specifically, and since we're doing classification, it tries to isolate similar or observations that belong in the same class. Let me box in all observations in this region, in this box. Let me box them in such that all the observations in here are in the same class. So notice, remember, that these cuts are going to be orthogonal, going to be perpendicular to an axis. And that makes sense because we go back to those yes or no, those questions with yes or no answers. They were only using one feature. In other words, it said for a feature, if the observation has a feature less than or greater than this value, move to this node. If not, move to the right node. So they're very simple questions based upon one feature. Geometrically, they look like this. They're performing orthogonal cuts. Those cuts are perpendicular to an axis. And you might be wondering, well, what if, can't I just use a more complicated question? Should I, why not consider a more complicated question? It would be a compound question, where if it's less than feature 1, this value feature 1, and it's greater than some value for feature 2, perform this split this way. Well, if we consider more complicated questions, then the model becomes intractable. With our number of possible candidates for questions is going to grow at a very large rate. It's going to be too great. The model's going to be too complicated. It's going to be too hard to train. So let's just consider these simple questions to try to box in our observations. Another thing that we see here with the decision tree model is that these models, you don't need to scale the data. There's no need to scale your data. And why is that? Why is there no need to scale our data when we're using decision trees? Remember, these splits, the questions is using to split the nodes are all based on one feature. It's not comparing other features. So because of that, there's no need to scale the data. For example, let's say we're going back to the iris data set and it says it decides to perform a split with a feature value of less, let's say the criteria is petal width less than 2.5 centimeters. Notice it doesn't consider any other features. It only considers one independently. Because it only considers one independently, there's no need, there's no criteria, there's no need that all the features have the same scale. It's not comparing two features at the same time. It's only using one. So because of that, there's no need to scale our data. And notice since the cuts are perpendicular, one way in which our model can have a better performance if our features are not correlated, not strongly correlated. If our features are strongly correlated, then it's going to be harder to separate our points. In other words, let's consider this example here. What if we have this example. We have two-dimensional space, and let's say our observations are, this is the red observations here. And this is, we have observations here, and this is the blue one. So we're trying to separate our two classes here, red and blue. If we're to use a linear binary classifier, we can see that we would draw a line this way. So notice we have a correlation with our features. However, if we were to use a decision tree model, then it could only perform orthogonal cuts. So it would probably perform a cut there, and then try to perform a cut there, and maybe there, or something like that. It'd be very difficult. But if we're able to rotate our space, rotate this space here, we apply a rotation, and when we apply this rotation, what ends up happening is that, you can imagine it, now the red points are right here, all exists above, and then our blue points are sort of the bottom half. So you no longer have this correlation, this strong correlation that made it very difficult to separate our points, separate our observations with a decision tree model. Another model, let's say like logistic regression, can just draw a line here, but decision trees will have difficulty because they're trying to create these boxes, these regions. But if we were able to rotate our space, then we'd have this situation here, and then it'd be very easy to create a partition this way. And we have perfectly separated our two classes. So here we see a downside with decision tree models. If the features are highly correlated, then it's going to be harder to perform the separation. So it's going to perform better when our features are not correlated. In fact, there are techniques we can use to generate new features that are uncorrelated. One example, one algorithm is principal component analysis. We'll discuss that algorithm in depth in future lectures. Now for models, one of the things we have to consider as well when we're learning about them is what are their training and time complexities. In other words, if I were to double my training points that I use to train the model, will I double the training time? Will it stay the same? Will it quadruple? What would happen? How does it scale? So we need to get a good idea for the training time complexities for our decision tree model. Let's go ahead and look at the prediction time. So let's see how long it takes to predict our points. And how does that scale? So let's say we're going to have a very deep tree. Let's go ahead and consider the worst case situation in which we have a very deep tree. In other words, where each node, each terminal node, each leaf is going to hold one observation. So we're going to keep on growing our tree until each training point has its own node. So we keep on performing the splits. So just draw my tree model here, perform the splits, and so forth. Well, going back to how many nodes does a layer have? So we say 2 to the depth of the tree will give us the number of nodes we have in that layer. So we have first layer 2 to the 1, 2 points, 2 nodes. Second layer 4 points, 2 squared. So the question is, how deep does our tree need to get such that if it were an even balanced tree, each training point would have a node? In other words, solve for D given this equation. So we solve for D given this equation. We take the log of base 2 on both sides. So we have the depth of the tree would be order n. Sorry, it would be log n. Log of base 2 of n. So now we know the depth of the tree. Then let's consider the time complexity to make a prediction. When we make a prediction for a decision tree, we start at the very root of the tree and we answer the questions, these yes or no questions, and we end up where we are. We end up in the terminal nodes, in the leaf of the nodes, and we use that to make our prediction. So, given the situation in which we have a balanced tree, and each trading point is going to be composed of one node, then we're going to have to ask a total of D questions, where D is the depth of the tree. If we have a tree that's 100 deep, then we have to ask, the algorithm must ask 100 questions to come up with an answer. So the prediction time complexity is going to be order log of base 2 of n. So that's the prediction time complexity for a decision tree model. So given this time complexity, that's pretty good. That means that as we scale the number of our trading points, the prediction time is going to scale as log of n. So that's pretty great. So our decision tree model, when we have a very large data set, will be easy to make predictions. We'll be very quick to make predictions. Now let's consider training time complexity. So going back to training the algorithm, remember what it must do. At each point, for each node, it must consider all P features and all possible thresholds for each feature. And the number of possible thresholds for a feature are going to be related to the distinct values for that feature. Now let's say we have the worst case situation in which we have n points and n distinct values for a feature. For example, feature 4, if we have 100 points, there'll be 100 distinct values for feature 4. Same thing for feature 3 and feature 2 and feature 1. The number of distinct values for each feature is going to be equal to the number of points we have. So to perform this initial split at the root, it must consider for all P features all of those distinct values. So P of n, it must consider P of n decisions. And this P number of decisions it must decide is the same as you go through the depth of the tree. Given this balanced tree that we're constructing, the number of points is conserved across the layer. So even though there are less points here, and there might be less candidates from the split, if we sum them across all the nodes in that layer, we'd get P of n as well, and P of n as well. So the total number of candidates it must ask to perform the split is going to be P of n times the depth of the tree, which we figured out before, which is going to be log of n. So the training time complexity is going to be Pn log of n. In other words, it's going to be linear with respect to the number of features. If we double the number of features, then the training time complexity is going to double. If we were to double our training points, well then it's not it's not linear, but instead it's going to be n log of n, which, yes, although it's not linear, it's not n squared. Log of n is still a pretty good time complexity. So training our algorithm, as we increase the number of training points, our training time isn't going to scale linearly with the number of observations, but it's not going to scale as n squared, which is a horrible training time complexity. It's going to scale as n log of n. So those are our training and prediction time complexities for the decision tree model. We'll again try to remember those, discuss them when we talk about other models, and compare them.